Let's recap before we do our cyclic case. Transition state. It's all about that transition state. We want to make this high energy species feel like it could actually happen. We want to make it reasonable. This is the hard part to get to. So what could we do to encourage it? So in other words, we need to have a leaving group. We must have a beta H, anti to the leaving group. Anti-coplanar. So that means you might need a Newman. We want a base that is strong because we're taking off an H. Because this is a concerted mechanism, we want to react right away and not sort of linger. So this is kind of similar to an SN2 in that way. We need a strong nucleophile for SN2. We need a strong base for E2. Solvents that are favored, similar to SN2, right? Polar aprotic, to keep our base strong, but to still solubilize it. So let's see how this looks when we do a ring system. E2 on a ring system. Okay, so one of our favorite bases is going to be T-butoxide, just because it's actually got that R group that's soluble, right? And it's not over the top bulky, unless the substrate is too bulky. So don't assume this still goes Zaitsev, unless you have sort of an exaggerated situation here. So we're going to be using T-butoxide a lot. So I'm intentionally using it here so you feel comfortable, because we're so used to thinking of T-butyl as a bulky group. So intentionally I'm using T-butoxide several times so that we're not stuck into thinking it's a bulky enough base to give us Hofmann. Okay, so we're going to go with Zaitsev in our answer choices. Now this is a ring system, so instead of drawing a Newman, we're probably going to need to draw a double Newman. Let's take a look at where we would do this though. Find your leaving group. So we find our base, TBUO minus, okay? Find your leaving group. There. Attached to your leaving group is the carbon we're going to call the alpha carbon. I'm going to zoom in on there. Alpha. Label the beta carbons. Beta, beta. Determine whether we want to go Zaitsev or Hofmann. Well, this is not over the top enormous. We don't have like big T-butyl groups coming off everywhere. We also have a borderline bulky base, so we're going to go Zaitsev. So between these two betas, if I call this beta 1, beta 2, beta 1 has 2 H's on it. Beta 2 has only 1 H. This would give us our Zaitsev product, right? If we put our pi bond here, it's more substituted than if we put it here. So we want this one. We want beta 2. So in order to see that it's anti, it helps to draw the chair. Anti-coplanar. Okay, so here's my methyl, right? And my H is down, my methyl's up. And that was my beta carbon. And here's my alpha carbon in question. My bromine is up, and that H is down. Look what I could do here. See that? That alone shows the anti-relationship. We're done. But if you're still not convinced, we're going to do this chair, but you don't actually have to do it every time. I'm just showing you so that we feel comfortable calling this the anti-coplanar conformation. So we have that diaxial arrangement of the two, of the leaving group and the beta H. So let's connect the carbons. Here's our beta carbon. Alpha's in the back. The back is joined by a down carbon. Fill in the staggered framework accordingly. Only things to draw in are the bromine and the methyl. Everything else is an H. Where's the methyl? It's on beta. Beta has an H on the bottom, methyl on the top. Who else has something? Alpha. Alpha has a bromine on the top, an H on the bottom. Everything else is H's, so that's easy. Here we go. Double Newman shows us, nice, beta H is anti to leaving group. So this proves it more thoroughly, but I'll show you another way you could tell without drawing all that. As long as the dashes and wedges are shown, we can use the consequence of this to help us kind of skip a lot of that extra drawing every time. Notice that the alpha carbon has a leaving group on a wedge. We prove that the dash is truly anti. Wedge and dash are opposite. So as long as you find a beta H on a dash, then that is the one you're allowed to take off. Okay, so here's our anti beta H for Zaitsev. If you want to do the Hofmann product, that would be the minor product. This is anti beta H Hofmann. You cannot use the wedged one. It's not anti. And it would not rotate to be anti because we're in a ring. Those relationships stay the same, right? So that's the difference with the ring system, is you can't change their relative orientation. So let's draw them both. Okay, so if we go down here, leaving group's gone, methyl is here. Do not put the methyl on a wedge. It used to be, why can't it be on a wedge anymore? This is sp2. sp2 is trigonal planar. No more wedges and dashes. Not a stereocenter anymore. Do not put it on a wedge. It's planar. It's wrong if it's written on a wedge, okay? All right, so major, that's our Zaitsev. Let's draw the minor, just so we're thorough. We left the methyl alone in the minor product. That means we took off this H up here. This was left alone. That better stay a wedge then. It didn't get touched. Still sp3 hybridized. This is where the alkene is now. So there's our minor, here's our major. Okay, watch out for those dashes and wedges. Make sure they're not drawn when they're not supposed to be drawn. Pause, give this one a try. Check your answer with me. You're supposed to pause right now. Are you pausing? Because I'm writing out the answer. Okay, did you get that? Only one product. No major, no minor. Only one possible. Why? Find your leaving group. We repeat these steps over and over again. Find your leaving group. Find the carbon attached. Name that carbon alpha, high alpha. Label the beta H carbons. Beta, beta. Draw in everything on beta. Draw in your H's. Okay, so now here's our beta H. There's a red beta H down there and blue beta H is up here. Those are equivalent. Now, or not really, but they're on the same beta carbon, which I'll label as blue. And I'll make this one the red beta carbon. Okay, so if I look at this one, it's not anti. It's syn. It's a wedge. The bromine's on a wedge. The leaving group's on a wedge. Syn to leaving group. Therefore, no E2 possible here. You say, but it would be Zaitsev. There's no possibility for that one. There's only one product. Leaving groups on a wedge, our only allowed one is this one. Anti-2LG. So in other words, that's not allowed, that's not allowed. Those are both syn to LG. This one is okay. That's the one we take off. That's why the alkene is there. That's why the dashed methyl remains dashed methyl with no alkene here.